Hey everyone, I'm Landon,
I'm Kellen.
And I'm David.
and this is our Impact Control System video. Recently, we were challenged by Professor Becknell to design an impact control system that would protect an iPad. The rules: it has to be repeatable, accurate, simple, and minimize randomness. Our objective is clear: build a system that could take a hit, collect data, and keep the iPad safe. This means brainstorming designs, testing prototypes, and nervously watching an iPad drop over and over again. In this video, we'll walk you through how we turn that challenge into an engineering process with 10 data points, a lot of teamwork, and maybe a few bumps along the road. This figure shows our house of quality, which we use to systematically translate functional requirements into quantitative design constraints. I'll explain moving left to right, then top to bottom. On the left side here are the functional requirements, what the system is required to do from a performance standpoint. These include easy to manufacture, easy to use, compact, within budget, decrease impact speed, minimize device fracture, slow fall speed, hold an iPad securely, and easy to install. Each functional requirement was given an importance weighting, reflecting how critical it is to an overall system success. Across the top are the quantitative design constraints, which are measurable engineering limits that define how the system must perform. Examples include fewer than 10 components, instructions under one page, maximum size of 12 by 12 by 12 inches, cost under $35, speed reduced by 5 meters per second, iPad displacement limited to 5 centimeters on impact, acceleration reduced to 2 meters per second squared, withstand a load of 3 pounds, install time under 10 seconds. Because these are all measurable, they allow us to objectively evaluate designs. The center of the house quality shows the relationship matrix, which links functional requirements to quantitative constraints. In this case, we use the 1-3-9 scale. 9 indicates the constraint strongly satisfies the functional requirement, 3 indicates a moderate relationship, 1 indicates a weak relationship. This helps prioritize constraints most strongly drive customer and system level needs. At the top is the correlation roof, which shows the interactions between quantitative constraints. A plus sign indicates constraints that reinforce each other. Minus sign indicates trade-offs or conflicts. Zeros indicate little interaction. This lets us anticipate design trade-offs early. For example, reducing acceleration may compete with size or cost constraints. On the right, we include the decision matrix against the datum and 3 competitors. Each competitor was evaluated against the same functional requirement using consistent weighting for fair comparison. The totals at the bottom summarize relative performance across all criteria. In this case, our datum was an OtterBox. The house of quality shows that our final design strongly satisfies the most important functional requirements while remaining within all qualitative constraints. More importantly, it provides data-driven justification for our design choices and highlights trade-offs before prototyping. This objective tree shows how our impact control system works. Our main goal is to protect the device during a drop. First, we slow the fall using aerodynamic drag from a frustrum-shaped body and a top hat air resistance, which reduces the device's velocity before impact. Next, we stabilize the system with structural elements like fishing line, popsicle sticks, and cardboard to prevent tumbling and keep the device properly oriented. Finally, we absorb the impact, using energy-absorbing materials such as sponge, styrofoam, and even vinyl foam to reduce peak acceleration on landing.
The first concept we came up with was having sponge with springs inside of the sponge layered with an iPad that could lay on top of it. The parachute would then connect to the corners of this sponge and spring bed. The sponge and springs would slow the impact's change in acceleration, while the parachute would slow the fall going into the impact. Slowing the fall would have less velocity that would result in less acceleration back into the iPad. The second concept was a cylinder with rubber bands going across its diameter and a parachute that connects to the top. The sponge and springs would also be at the bottom of the cylinder concept as well. The sponge and springs would now work with the rubber bands to slow the rate of acceleration change, while the parachute would work as the same in the first concept and slow the fall. The third concept, which was the one we ended up choosing, would have a frustrum shape and rubber bands would go across the frustrum. The sponge would be at the bottom but would not have springs, since after looking at the springs and sponges, the springs did not assist in slowing down the change in acceleration but actually worked the opposite and ended up making the change in acceleration greater. We still, instead of having a parachute, would have another way to slow the fall, which would be a kind of roof that is slightly spaced from the top of the frustrum that would have edges that go at an angle downward. That way it would be redirecting the airflow and slow the rate of the fall. There would also be a weight inside the rubber band structure to hold it to keep it balanced as it falls, but after we found out that it only falls 2 feet, we decided not to include the weight in the final concept because it would just be adding more weight into the final design, which would result in greater forces. So since we didn't have to drop it as far, we didn't have to worry about it tilting over, and so the weight seemed unnecessary.
The CAD model represents the ideal design for the project. It makes full use of the 12 by 12 by 12 inch space given and maximizes the sponge space. There are 2 gray strips of black rubber foam weather seat tape, which was imported material, which both go on the sponge layer to provide extra cushion. The sponge sits at the bottom and connects to the base of the frustrum-shaped enclosure. Inside the frustrum, there is popsicle sticks that connects to rubber bands, which creates a base layer for the iPad to sit on. In the side of the enclosure, there is a slit for the iPad to go directly above the rubber band layer. At the top, there are supports made of popsicle sticks to hold on to the roof above the top of the frustrum, allowing air to redirect and slow it while it falls.
This is our final product design. Our final product is derived from the CAD models, but we had to change some of the different parts of it because we needed to fit the constraints. Our first constraint we needed to fit was a 12 by 12 by 12 cube. So in our CAD model, since it was idealized, it perfectly matched a 12 by 12 by 12. However, because when making it, we can't be exactly the same as an ideal situation, we had to cut off some of the foam from each side, all 4 of them, meaning that we could not include 2 strips like in our CAD models. We just have 1 strip of foam and the sponges are cut. Then, because we also couldn't fit at the top, we made this an 11 by 11. That way, if we were off-centered slightly, which you can see slightly off-centered, we're not matching, we're not going over any lines, we're staying within 12 by 12 by 12. And then on the inside, there are now popsicle sticks underneath each layer of sponge, and then there's popsicle sticks, more popsicle sticks around the top. That way, when the rubber bands are pulling in, it doesn't implode on itself. Since we supported the outsides, we could then add more rubber bands to the cushion here. And so when making the cushion, we would drop a phone over and over until we got it to where the phone did not hit the table. The phone weighed about the same as the iPad, and it was more centered in one spot, meaning that it would represent the iPad well. So we added a total of 24 rubber bands to each side. They are solely on the sides. That way, the iPad, since it would sit long ways, it's not touching the sides and would not risk hitting the popsicle sticks that are holding the rubber bands to the walls. The iPad will slip in this slit and then lay down sideways like this.
This testing was done by taking the iPad, hitting start, and slipping it into the side opening of the box. Then dropping it with the bottom of the box even with the 2-foot marker. Once it fell, wait 4 to 5 seconds after the impact to allow the rubber bands to settle and create space in the data between when you pick it up and the original drop data. When you pick it up, you flip it over, hit stop test on the iPad, then you push the iPad out of the opening. Then export the data using an Excel sheet. Then you cut the data to half a second before the first acceleration of 9.8 meters per second because it signifies the drop. Also, 1 second after the initial drop.
In the graphs of acceleration, you can see that directly before the drop, acceleration is 0 meters per second squared. Once it is dropped, it falls at 9.8 meters per second squared. The impact is the first large spike, but it isn't the only one. This is because the rubber bands holding the iPad then push it back upward, giving a smaller acceleration spike. Then, once the iPad falls back down inside the device, it falls again at an acceleration of 9.8 meters per second squared. It repeats this bouncing action until the iPad comes to rest. There are 10 points between the two times where it is only acted on by gravity, which is what is defined as the impact in the research we did. This is because when gravity is the only force, that means it is no longer in contact with the rubber bands, which signaled the start and end of the impact. The velocity graph is then derived from the acceleration graph by using this formula. The position graph is then derived by using this formula. The force graph is the acceleration graph times the mass, which is 0.763 kilograms. This is the total of the iPad plus the device, which are both 0.460 kilograms and 0.263 kilograms respectively. Using ChatGPT along with other sources, we found that minimizing noise meant that we need to cut down on the extreme angles of the graph. To do so, we ran it through different codes and found that this graph represents our data with a lower amount of system noise. The peak accelerations were then compared to each other in order to test the difference between each test. The first test of the three had a peak of negative 154.459. The second had negative 153.359, and the third had negative 152.365. When analyzed, the average was negative 152.728. with a standard deviation of 0.5486. The requirement was for any data point to be within 5% of the average. The farthest from average we had was 0.4%, which is much less, showing it is extremely repeatable.